Hi, in this lecture, we are going to learn more about the respiratory buffers. You previously learned about the chemical buffers. Remember, the chemical buffers are the fastest ones to jump in. They work within seconds to minutes, but they can be quickly depleted. Our respiratory buffers are considered a physiological buffer because they can take that hydrogen ion and convert it into water. So they tie it up in the water molecule so it does not affect the pH. However, this will only work when you have a functioning respiratory system. You can't have any respiratory disease or issues with the respiratory control centers in the brain, or the lungs can't buffer. And it is limited a little bit by the availability of bicarb. So the first thing we have to do is just review what you previously learned. You should recognize the slide. It came up in the respiratory system PowerPoint. We have our typical equation. If we take CO2 and we combine water to it, it forms carbonic acid, and carbonic acid will break down into bicarbonate ion and hydrogen, and the equation can go either direction. So what if the lungs are diseased? So first we have to talk about the lungs if they're the cause of the problem, because as you learn acidosis, alkalosis, you'll be learning about the kidneys and the lungs, and it's very important that you understand when the lungs are the problem or the cause, or when they're the solution. When they're the cause, the issue is something wrong in the lungs. So perhaps you have slow, shallow breathing, you're retaining CO2, maybe you have pneumonia or emphysema, or you have a drug overdose, barbiturates, morphine, and so you're hypoventilating. What's happening is you're not getting the CO2 out. We know our normal range of CO2 is 35 to 45 millimeters of mercury, and this is arterial blood. So if my CO2 levels go up in my blood, then this will push this equation to the right. So I will actually generate more carbonic acid, which will break down and release more hydrogen ions. So when my PCO2 goes up, remember that's called hypercapnia, that will produce more hydrogen ions, which will then lower my pH, and I will be in respiratory acidosis. So my lungs are diseased, they are the problem. That's why you see the word respiratory, and I'm in an acidosis. If I'm hyperventilating, maybe I'm having a panic attack or a drug overdose, now I'm getting rid of CO2, my CO2 starts to fall, I need to maintain my levels between 35 and 45. So now if my CO2 were to fall, I need more. So now this equation is going to be pushed to the left, and I'm actually going to use up hydrogens because they're going to combine with any bicarb to make carbonic acid. So it can go up and release CO2 and try to raise my CO2 levels. And so the issue here is respiratory alkalosis. So when the lungs are the problem, we will see the word respiratory in front of it. However, having normal, nice, healthy lungs is very, very important as a buffer. So if they're going to fix it, then what we're going to look at now is same equation. We have our lungs and our kidneys, but now our lungs are normal. We have no respiratory disease. We want to see how they fix it or how they buffer. So if my pH should fall, I have too many hydrogen ions. So there's an addition of hydrogen to my circuit. Maybe I'm making more lactate. Maybe I'm not getting rid of hydrogen in my kidneys. Maybe there's more pyruvate, or I'm making ketoacids. I'm in ketoacidosis. So now when I have more hydrogen ions, that will combine with the bicarb that's available. Remember, I'm always trying to maintain that 20-to-1 ratio. When I combine those, I'm going to form carbonic acid, which will go to my lungs, and that will release the CO2, which I will exhale. So my lungs are going to buffer because they're going to breathe faster and faster to get rid of the CO2. So they're fixing it in this case. So in response to my pH dropping, my respiratory rate goes up to get rid of the CO2. And if I were to measure my CO2 levels, they would be normal, or my CO2 levels could actually be lower than 35, because I'm getting rid of more of it because I'm trying to buffer. So you can't just memorize numbers and say it's this or that. You have to understand what's going on. In this case, my CO2 falls because my lungs are buffering all those acids that are produced. If I'm in an alkalosis situation, now I don't have enough hydrogen ions. I need to maintain that. So now the equation goes to the right because I'm concerned with the hydrogens. Well, the only way to get more hydrogen is I need more of this carbonic acid because that's where they're coming from. Well, the only way I get more carbonic acid is if I hold on to CO2 and water in my blood. So now I want the CO2 in my blood. I don't want to get rid of it. So I'm going to decrease my respiratory rate to try to hold on to CO2 because I want it to go up in my blood so I can make more hydrogen ions. So when I'm in an alkalosis state and my lungs are trying to fix it, my PCO2 levels might actually go up because they're trying to fix it. So my CO2 levels are going to give me a hint as to if my lungs are the cause or the solution. If they're the cause, it fits with the equation we looked at. When my CO2 goes up, right, I'm going to generate more hydrogen ions and have respiratory acidosis. But when they're fixing it, my CO2 levels are going to change because my respiratory rate changes because I'm trying to buffer those hydrogen ions. And so it's important that you can understand if they're causing the problem or they're fixing the problem by understanding same equation. One side, we're looking at how the hydrogen ions push or pull the equation to affect the respiratory rate. And when the lungs are the problem, we're looking at how the CO2 pushes or pulls because the lungs are the problem. And we'll be looking more at this in our last lecture when we try to put all of this together. So that wraps up our respiratory system buffers.